Hello, good afternoon, everyone. You are welcome to my class. We want to continue from where we stopped. Today, we are going to be talking about free span movement and actual span movement. All right. Now, from the structure we'll be analyzing, is actually beam one. All right. So, um, this was where we stopped in our last class. We want to continue from the span movement. All right. Now, first thing first, when we're talking about span movements, all right, we'll talk about the free span movements. Uh, so, we call it free span movements. Free span movement, right? In this case, what is free span movement? Free span movement is the maximum movement that occurs when a beam is simply supported at its ends and is subjected to uniform loading. All right. For instance, we have this one. All right. This is simply supported. So the frame span movement now assumes that at its ends they are supported, right? And that at this support it rotates or it can be deflected. So free span moment is the maximum moment that occurs when a beam is supported at its ends and is subjected to uniform loading. That is what free span moment is talking about. So in this case, we have a continuous beam, right? At every span, free span moment assumes that at every span is simply supported. That is what free span moment is talking about. And in this case, we cannot use free span moment to design a structure. Instead, we use actual span moment. Now, what is actual span moment talking about? Actual span moment actually takes care of the support condition, the actual support conditions. All right, it talks about the degree of fixity or continuity of this beam. Right, it's actual span moment that you actually use in designing for a continuous beam. Now, what is the formula of what's the formula of calculating free span moment? Free span moment, I can denote it to be MO. All right, MO is our free span moment, is equals to W L squared over 8, right? Where the W is our load, then the L is the span, then, so that's the formula for free span moment, okay? Whereas actual span moment, which I will denote as MA, is equals to free span moment, all right, minus support moment over 2. Now, the difference between this and this is that free span moment assumes every span to be simply supported, while actual span moment take into cognizance the support loading, the reaction from the support, the actual support condition of every beam. So it is very, very accurate when you use this formula, when you use actual span moment to design for the beams instead of using this. All right. So this support moment reduces the effect. All right. This support moment reduces the effect of the free span moment. So, when you use this particular moment designed for a continuous beam, is very, very accurate. So first thing first, you solve for free span moment. All right. Now, free span moment. Free span moment A and B, you can say N A B is equals to WS squared W square, W in this case is 35.55 kilonewton per meter. Alright, so if you don't know how we got this one, go to my previous class. Everything is there. Now W is 35.55 multiplied by 2.025 square over 8. If you compute this, let's quickly compute. We're going to have 35.55 multiplied by 2.025 square divide 8. This one will give us 18.22 kilonewton meter. 18.22 kilonewton meter. Alright, that is for free span moment E between span A and B. Now we also talk about free span moment BC. Alright. Now in this case, our load is different from this first load. Alright, so and our span is different. Between B and C, the span is 4.1125, then the load is 40.93. So if you impute values in our formula, we have 40.93 multiplied by 4.1125 square over 8. What this one will give to you will be 40.93 multiplied by 4.1125 square divided by 8. This one will give me 86.53 approximately. 86.53 kilonewton meters. Okay, now later you see the difference between, you see why it is more accurate when you use actual span moment. Now free span moment here, you know, it assumes that at every span is simply supported. So MBC here is equal to 86.5. This between C and D, the span is equal to BC is equal to CD. Alright, the span is the same and the loadings are the same. So this means that BC is equals to MCD equals to 86.53 kilonewton meters. Alright, if that is solved, we are done with free span moments. Okay, now the next stage is to go for actual span moments. Actual span moments. Now I gave a formula before. In this case, between A and B, actual span moments A and B is equals to MO AB minus MA plus MB all over 2. Okay, now when I impute the values here, I now have that MAB is equals to MAB free span moment AB will be equal to 18.22. Alright, so when you impute the value, you have 18.22 minus, what is our MA from here? 0.00 plus MB is 39.01, right, over 2. When you compute, what will this one give to us? When you compute, we are going to have 39.01 divided 2 minus 18.22. This one will give you minus 1.22 285 kilonewton meter. Let me write it very well. Minus equals to minus 1.285 kilonewton meter. Now, when you are solving for span moment, if it is positive, you know that it's a sagging moment. All right. All span moments are assumed to be a sagging moment. All right. But when you now design, calculate, analyze, and discover that you are having a minus sign, it shows that this means that instead of having a sagging moment at this span, we're having a hugging moment. All right. A hugging moment. It means that the reaction is at the top. The reaction is at the top. So this means that when we are reinforcing this span, is going to be at the top. All right. So this is a hugging moment. All right. So we proceed. We proceed here. Let me clean this. We are done with actual span moment AB. So we are moving to actual span moment BC. All right. This is equal to free span moment BC is what? 86.53. Put it there. 86.53. All right. Minus MB. Support moment B is 39.01 plus support moment C. All right. Is 76.76 over 2. Remember, it's like this, equal to. All right. So when you compute this, we're going to have 39.01 plus 76.76 divide 2 minus 86.53. This one will give me 28.65 kilonewton meters. Okay, so recall that this one is actual span moment AB. So I know this one already, 80.22. So when I have that actual, that was the one I cleaned over was free span moment BC. We've gotten our actual span moment DC to be this. Now the next is to solve for actual span moment CD. Have MACD is equal to free span moment BC is equal to free span moment CD. So we're going to use this value 53 minus, now we have MC to be 76.76 plus MD is equal to 0.00 over 2. Okay. Now when you solve for this, we have 76.76 divided 2 minus 86.53. We now have 48.15 goes to 48.15 kilonewton meters. So you can see that when you solved for the free span moment, MBC was equal to MCD equal to 86.53. Now, actual moment now, taking into cognizance the support moment, it has reduced the moment, free span moment between B and C and D. Now, actual span moment between C and B and C is now equal to 28.65. Actual span moment between C and D is now equal to 48.15. Alright, so this is the correct value, the accurate value to design for your beam. Alright, now in my own case, when I'm designing manually, I use maximum span moment to design my beam and maximum support moment to design my support. Alright, but when I'm using, I normally use a software, Quicksilver series. Alright, but for calculation sake, for the sake of this lesson, we are going to be using maximum span moment and maximum support moment to design for this beam. So the next stage is to draw the bending moment diagram. All right. Next stage is to draw the bending moment diagram. First thing first, I have to write the moments out. Let me see. Let me write it here. Actual span moments NAB is equals to minus 1.285 kilonewton meters. Right, MBC is equals to 28.65 kilonewton meter. Then NCD is equals to 48.15 kilonewton meters. Okay, so I cannot clean this board to draw the bending moment diagram. Okay, let me draw this one. Now, bending moment diagram, use a graph. Please, you must use a graph to draw your bending moment diagram. Alright, so this is point A, this is point B, this is point C, and this is point D. Okay, now recall that the span between B and C is equal to the span between B and C is equal to the span between C and D. Alright, so we draw the bending moment diagram from the results of our analysis. Alright, now we have that at support A and support D, the moment is always equals to 0. Okay, now between A and B, we have a negative sign. Now, instead of it to be a sagging moment, it's now a hugging moment. So we say from here to here is hugging. All right. Now, support B is 39 point. Okay, it goes like this. All right. I can take this one to be minus, let's say 1.285. Here we have 39.01. Right, now between B and C, BC, we have 28.65. So let me draw 28.65. It's not as deep as 39.01. So now we have point C to be 76.76. So this will go all. Remember, this is just a freehand sketching. All right, if you want to draw your bending moment diagram, use a graph. Okay, now we have point C and D. The span moment is 48.85. So it comes like this, goes to 0, because at support D we have the moment is equals to 0. So this is how the beam will react when loaded. All right, this is how the beam will react with the load is subjected to. Sorry. All right, the load subjected to. So I will put in the value here. This is 76.76. This is 48.15, all in kilonewton meters. All right. This is how this beam will react. This is how the beam structural member, the beam will react, all right, to the loading. So, right, if you plot your graph, you have more accurate diagram. So that's it. So the next step now is to design. I have said before, when I'm designing for support moment, I will use maximum moment. When I'm designing for sake of this class, when I'm designing for span moment, I will use the maximum span moment. So let us first of all go solve for the support moment. Design. All right. I've got this on support. Maximum moments is equals to 76.76 kilonewton meter. And of course, you know that K is equals to M over FCUBD square. Alright? So if you have been following me before, you will understand this formula. Now we want to calculate for the lever arm, then go to the area of steel. Now, of course, you know that FCU is characteristic strength of concrete. Alright, we are using 20 Newton per millimeter square. Alright, and now here our beam, we are taking it to be 450, the depth. Alright, the D is equals to 450 minus 16 over 2. In case may be. Or no, sorry. Concrete cover minus 20 minus 16 over 2. Assuming we are using 16 mm. Alright, so we're now going to have 450 minus 20 minus 8 is equals to 422 millimeters square. Millimeters, alright? Our D is equals to that. Okay? Our D is equals to, sorry, the space is not much. Our D is equals to 450, which is the height, minus concrete cover, which is 20. I took 20 concrete cover, minus 16 over 2. Alright, minus 16 over 2. Okay, because if you have a beam here, alright, the concrete cover, this is 10 mm. So 10 mm. Ooh, screening. Right, 10 mm. Alright, this is it. Concrete cover from here to where this what's it called? This concrete cover 20 from the formwork to the stirrup is 20. That's concrete cover. Then half of the reinforcement, which is 16 mm, which is what we have there. Okay. Now I don't think that is clear enough. Let me make it simpler. Assuming we have a beam like this, we have the stirrups, then we have the reinforcement, for instance. Now, the dimension between the formwork and the stirrup is what we call the concrete cover. That's the cover. Then we now have the stirrup. The diameter of the stirrup is assumed to be 10 mm. Then the reinforcement is assumed to be 16 mm. All right. So that is what we have there. So 450 from here to here, which is the height, is 450. All right. We're now saying 450 minus concrete cover minus the stirrup minus half the steel. Okay, that's what we're having there. So the H is equal to D is equals to, when you compute that, we're going to have 450 minus 20 minus 8 minus 10. That's 412. We're going to have 412 mm. Okay, that's what we have here. Okay, now we also have B. From here, we'll talk about flange width of beam. All right. Now, from our design, from the beam 1, all right, or if you have a design like this, this is a design. You have this as a design. Now, this is an L beam. All the surrounding, they are L beams. All right, this is an L beam. Then why the one inside, they are the T beams. All right, so for an L beam, the formula of flange width is equals to BW, weight of bear, width, web width plus 0.7 span over 10 for an L-shaped beam. Then for a T beam, we're going to have BF is equals to breadth of the web plus 0.7 L over 5 for a T beam. All right, but in this case, this is an external beam. All right, it is an L-shaped beam, so we are going to make use of this formula to calculate the flange width. All right, so for instance, when I'm talking about flange width, I'm talking about an L beam, an L-shaped beam. All right, L-shaped width, this is BW. From here to here is BF. All right, that is what we are talking about. Flange width of beam. All right, this is the web. It's always taken to be the width of the wall, which is 225 in our case. Okay, so now when you compute that values, we are going to have that this BF is equals to 225 plus 0.7 multiplied by 2. Okay, yeah, this is a okay. This is a support. This is a support. Sorry, this is a support moment that we are designing. So for support moment, the width is always W. Is always for support. The width is always equals to the width of the wall, which is 225. All right. The one I was doing just now, I was trying to put in just now, is the width when you are designing for the span for the spans. Okay, now but here we are talking about the support. All right, we are talking about the support. So you recall that the maximum moment at the support we are using is 76.76. So the width of the support is the width of the block, which is equal to 225. So when you impute that in this formula, we are going to have that K. We are going to have that K is equals to 76.76 exponential 6 over 20 multiplied by 225 multiplied by 412 squared. Okay, let me include this one. That's our D is equals to 412 millimeters. Okay, now when you solve for this, K must be less than or equals to 0.156. So when you solve for this, we're going to have 76.76 exponential 6 divided by 20 multiplied by 225 multiplied by 412 square. This one will give me 0. This is equal to 0.100100. All right. So this is less, which is less than 0.156. This is okay. All right. So the next step is to calculate for our LA. All right, which is equal to 0.5 plus 0.25 minus K over 0.9. Okay, in this case, what is our K? We have, since this value is less than 0.156, you use the lesser value. All right, so what is our K? Let me clean because the board is not wide enough. Our K is 0.100 over 0.9. So when you solve this, which must be less than, this must be less than or equal to 0.95. Okay, so let's quickly solve this and see if the result will be okay. Now we have 0.25 minus 0.1 divided 0.9 square. So plus 0.5. So this one will give me, LA will give me equal to 0.873, right, which is less than 0.95. So you use the lesser value. Okay, now the next step is to calculate for Z. Z equals to LA multiplied by D. Is equals to LA is equals to 0.873 multiplied by 412. This one unique. That will give us 0.873 multiplied by 412. This one will give me 359.68 millimeters. All right. So the value of our Z is equals to 359.68 millimeters. So you know what we're calculating for today. What we want to get is our area of steel. Now we are getting to the final. The area of steel here, we're going to have AX, area of steel required will be equal to moment, maximum support moment, 0.95 F YZ, where our Fy is the characteristic strength of our steel, which is normally taken to be Fy is equals to 410 Newton millimeter square. Alright. In our BS code, I explained this before. In our BS code, we have 460, but the strength of steel in this country is now 460. We are using 410. So let's put the values, and we have 76. That's the AS. Okay, let's say equal to 0.76 exponential 6 over 0.95 multiplied by 410 multiplied by our FYZ 359.68. So what would this one give to us? Let's be clean. When you compute, you're going to have 76.76 exponential 6 divided by 0.95 multiplied by 410 multiplied by 359.68. This one will give us 5 AS required will be equal to 548 millimeters square to the nearest whole number. Alright, so this is our AS required. So we've gotten this AS required. You will now go to your BS code to get the number of steel that will be required here. Alright, in this case we have two areas. In this case we have two areas of steel that we make use of. We have this one is for spacing. Alright, this one is for spacing. Okay, this one is for spacing, while this one is for the numbers. This one is for number of reinforcement needed. Alright, number of reinforcement needed in beam. This one is for spacing in slab. Here we are making use of numbers, alright, because we are designing for this. We are designing for the beam. Alright, so our area here we have AS. If you go to the beam, we said today we are using 16 mm, so we have area required to be 548. So in our area table, we'll look for 16. Alright, the one that is closer, a little bit higher than area required, which is 603. Right, 603. Sorry, 603. This is 16 mm. Alright, 603. You can see it here, 603. So area required is 548. So can I come here and say provide 3y16 millimeter diameter bars top, because this is a hugging moment. The reaction is at the top. Alright, so we have done that for the support moments. Alright, we have done that for the support moment. So this is top reinforcement, 3y16, and our top reinforcement. So anytime you are seeing detailing, you see structural design, and they are saying 3y16 top, this is how the structural engineer analyzes to arrive at 3y16. This 3y means that at this top level you provide 3 number of 16 mm. Alright, so you must analyze to know the reinforcement that will be adequate in the support. So we are also moving to our span moment. Alright, we are done with this. So we are moving to our span moment. Span moment. Span. Alright. Designed for the span. Our maximum moment is equal to 48.15 kilonewton meters. So the same process, the same way you also provide for the span moment. Now we proceed. K is equals to M 48.15 times 10 raised to the power 6 over FCU, which is characteristic strength of concrete, take it to be 20, multiplied by, in this case, we are making use of BF, flange width of beam. Alright, so this was what I was trying to calculate in that when I was designing for the support. Okay, multiplied by our 4112 square. Okay, now we want to get the value of our BF. BF is equals to 225 plus 0.7 multiplied by, let me use let me use 4 multiplied by, because this is the maximum moment, 41125.25 over 10. This one will give us, when I solve, 0.7 times 4112.5 by 10 plus 225. That's 512. Let's say 513 millimeters. Right? That is our flange width of beam. Alright, so this is what we're going to be making use of right now. So we've gotten our width of flange width of beam. So please let me clean up because the board is not wide enough. Alright, we're having a 513. So let me write it here. BF is equals to 513 millimeters. So let me clean this one off. So when you impute the value here, we are going to have BF 513 multiplied by 412 square. This must be less than or equals to 0.156. Alright. So we also calculate this 48.15 exponential 6 divided by 20 multiplied by 512 multiplied by 412 square. This is equals to 0.0. This is equal to 0.027 or 28 approximately, which is less than 0.156. So we'll make use of the value of K. Now go to LA is equals to 0.5 plus square of 0.25 plus 0.028 over 0.9. Sorry, this is minus, minus, this is minus, not plus, sorry for that. So we now have, we solve for this must be less than or equal to 0.95. So if you solve for this, we are going to have 0.25 minus 028 divided by 028 divided by 0.9. We're going to have square answer. Loss 0.5. This is 0.967. 0.967, which is greater than 0.95. So we adopt this value. We use 0.95. All right. We use 0.95. So when you move ahead, you solve for LA. LA is equals to Z. Z is equals to LED, which is equals to 0.95 multiplied by LED 412. This is equal to 0.95 times 412. Will give us 391.4 millimeters. Okay, so we're still going to continue. Then we'll now have our AS required to be equals to M, that is 48.156 over 0.95 multiplied by 410 multiplied by 391.4. Okay, when you solve, you are going to have 48.15 exponential 6 divided by 0.95 multiplied by 410 multiplied by 391.4. This is equals to 315.84 millimeter square. So here we are going to provide, okay, let me clean. Here we are going to provide, let me go to the table. All right, so here we are going to provide, the area is 315.84. So we're going to go to Y16, trace it down where we have, okay, we have 402, which is greater than 315. So it means that it's 2Y16 we are providing. So we provide 2Y16 millimeter diameter bars bottom. All right, so this is 2Y16 for this span. So it means when I say we use maximum span moment to design for this span, so it means that from here to here is 2Y16 bottom, 2Y16 bottom. I can still use 2Y16. Or no, yeah, I can still use 2Y16 here, but remember, this is top reinforcement. So, but this 2Y16 will serve as a hanger bar in this. So that is that for that. Assuming I want to detail this beam. Assuming I want to detail this beam, alright, we have this beam to be like this. We have this beam to be like this. Don't mind my sign. Alright, we have the beam to be like this. This is detail enough for instance. Alright, this is the depth of the beam. You have from here to here. And you also have from here to here. You also have from here to here. For instance, okay. Now this is our stirrup. This is our stirrup. From here to here. From here to here stirrup. From here to here stirrup. And here stirrup. And we said the top reinforcement here is 3y16. Alright. Top reinforcement here is 3y16. 3y16. So then the bottom reinforcement here is 2y16. Okay. The bottom reinforcement here is 2y16. So when you want to provide, assuming it goes like this, right? This one goes like this. This one goes like this. Sorry. This one goes like this here. This one goes like this here. Now, assuming the span of the beam is more than 12 meters, you will break it, but this one is less than 12 meters. All right, this one is not up to 12 meters, so you can use one full length of beam if you are using the same number of bars. All right, so this one now becomes your 3y16. This one becomes your 2y16. All right, so the cross section will have to be like this. Cross section will be like this. Then you have the stirrup. The top is 3y16. Then the bottom is 2y16. Right? But remember, it's an L beam. Alright, it's an L beam. So this is how you design your beam. Okay, an L beam. Yeah. So this is it. From here to here is 450. From here to here is 225. Alright, so this is how you detail your beam. Alright, so we are done with this beam, but we are not through yet. We are done designing the moment. But the next time we come, the next class, we are going to talk about the shear force. Alright, it is the shear force that you use in spacing your bars. I will not tell you the size of steel to use for your stirrups. Okay, thank you very much. We are done for today. In our next class, we'll be designing for shear. All right, we'll check for shear. Okay, but for now, have a nice day and God bless.